See, it's only going to, well, oh, okay, yeah. So there's more hidden. I mean, the thing that's hidden is in the domain of this stupid map. See, the domain is vector space of contact vector fields. Well, that's terms and there's terms and conditions there. I mean, that means that it's not just any old vector field. It's a vector field which is what? Right, which means, oh, oh. Goodness gracious, that's actually a calculation.
Well, but we're doing the inverse, right? So we only need to, because the codomain is just all speed functions from R3 to R. And we're only doing the inverse.
But I have to produce something here which is I'm supposed to pick the vector field which is, it has to be an element of the chi u alpha. In other words, I have to also, that has to be subject to the terms and conditions. This has, if I call this thing v, I need that the Lie derivative with respect to v of alpha is equal to g times alpha for some g. So what's that even mean? I mean, maybe that's not too bad here if we actually get into the details, right? What is L sub v of alpha? What's that? Well, I can tell that much from the formula for alpha, because tracking back, this A could have been anything. The fact that A can be anything allows me the flexibility to put this vector field going backwards into the appropriate space of contact vector fields. But it doesn't show up in the formula explicitly. Like, there is a way for a given space of writing this just in terms of two parameters which show up over there. But we haven't done that. Like I said, the devil's in the domain. Every once in a while, I assign a problem like this in linear algebra, and it blows people's minds. Do you remember it? It's like, find coordinates on a subspace, a two-dimensional subspace of a three-dimensional space, where I give the two-dimensional subspace in terms of ABC. But the thing is, A, B, and C aren't free, because they're ABC characterizing a point in two-dimensional subspace of a three-dimensional space, which means that there's terms and conditions. But the terms or conditions are hidden in the statement that ABC, with the appropriate vectors weighted, is in the subspace. This is like that.
So should it be F of P?
Cartan formula, right? Which is what?
I of V d alpha plus D of I d alpha.
So is any of that 0? Oh, we don't know it's the Reeb field. I just don't want to do it. I'm sorry. So anyway, I mean, at this point, I'm kind of stuck without filling a board with calculations. I chose a poor path. All right, but I think we have done enough that we can now at least try to understand the sort of penultimate, well, it's not the penultimate, but it's nearly the final example in here. And to me, this maybe this will give you a sense of what's actually going on here. So in my way of thinking, this sort of naturally leads to studying. I don't know if what I'm about to say really is strictly part of contact geometry. I don't have a good enough sense of what's what. But it seems to me the study of exterior differential systems is somewhat related to what we're doing. I don't know if it's the same thing. I don't have a good sense of the layout of the land at the moment. Let me just do this example here, and then I'll say what I have to say about that, and we'll be done for today. So here's the example 6.7.22. Consider the first order partial differential equation, partial u, partial x, plus partial u, partial y, plus u equal to 0. And we have initial conditions, u of x comma y equals to 1 on the unit circle. Now, so what's he do? He says, we can represent this as the 0 set S of f. F is a function from R5 to R. And this has coordinates x1, x2, w, m1, m2. All right. Given by what? If we want to represent the given partial differential equation as a 0 set of a function on this 5-dimensional space, what is that function? You guys can tell me that, right? Travis, take a shot. It depends on whether, to me, it depends on whether the m1 and m2 are the derivatives, or if the x1 and x2 are the derivatives. I think he means m1 and m2 like slopes. So I think this translates into m1 plus m2 plus w equal to 0. Well, there is no explicit x1 and x2 up here. There's derivatives with respect to x. And so I'm pretty sure that x1 is equal to x and x2 is equal to y. Okay, good. Checking. Now, his use of the letter m stems with his initial motivating section earlier in the chapter. He says, okay, all right, now we're going to get nuts. For the Cauchy data, we will consider the domain minus pi over 4 to 3 pi over 4 along the parameterization. Seems odd. Okay, whatever. Let's taking a ride here. So he says u is equal to minus pi over 4. I mean, it's just an odd choice. I get that gets you pi. Just not sure why he's doing that. And phi of s is equal to cosine s sine s. Great, that's a circle. So this parameterizes what? I mean, it parameterizes the circle, at least half of it, right? And, well, there's a reason he did it. He says, we've chosen the domain in such a way that the vector field on R2, given by VF, equals to fm1 partial x plus fm2 partial y plus, oh, that is equal to what? Partial x plus partial y. He says that this is nowhere tangent to phi of u. Is that clear to you guys why that is? Phi of u is a circle, right? Actually, that's clear. That is the radial vector field. It points out, so it's transverse to the circle's tangent, right? I mean, that's the usual thing, so I can even draw a picture of it. We're going from minus pi over 4, right? Minus pi over 4 to 3 pi over 4, which is what, like, so it's something like, that was sort of, kind of, right? Anyway, there's the parameterization, and this partial x is, well, it's like that, right? So it's nowhere tangent. I still don't know why we care about that. And we define g by g of s equals to 1. All right. And he says the Lee's characteristic vector field, x sub f. See, that's the thing I don't think we ever got to, did we? Did we define the Lee's characteristic vector field, what that was? I don't think we did. Curses. I think it's a vector field which is given to exist relative to the given contact. Okay, it's definition 6.718. It's earlier in this section. The characteristic vector field for the partial differential equation represented by the smooth function, like we just did, is x tilde f. The horizontal part of the gradient, blah, blah, blah. Oh, goodness gracious. Is that the, but oh, stink. All right, I just found it. Sorry, guys. Fine print. Here it is, here it is. I was trying to avoid writing everything out, but I see I have failed you guys in that regard. Come on. So this whole section must start with a big old system of partial differential equations, yeah? Come on, out with it. Anyway, definition 6.7.18, it defines, I won't write down the details, but it defines f, x sub f tilde And then we're told that x sub f tilde is related to the x sub f. You take x sub f and you subtract f times the Reeb field. Well, he has a sub 1 on it. It's the Reeb field for alpha 1. You might ask, what's alpha 1? Right? Alpha 1 is a contact form, which has been discussed earlier in the section. So sorry, guys. All right, let me get on with it here. So hopefully I'll write enough here that we can at least understand it. X sub f is minus partial x1 minus partial x2 plus w partial w plus m1 partial m1 plus m2 partial m2. All right. So this is Lee's characteristic vector field. Let me give you the big picture of the method. You take a partial differential equation. You find the corresponding characteristic vector field for it on a higher dimensional space. Then what you do is you find integral curves to that vector field, right? And then from those integral curves, you can find what your solution was to the original PDE. What I have not explained worth anything is how to find the vector field, right? But there is a method. And it's probably not that bad if I just taken 30 minutes to really write out the start of this section carefully, okay? Anyway, so if we're looking for an integral curve to this, what system of differential equations do we have to solve? 5, right? So 5-dimensional space. What are the 5 differential equations? We got to solve x1 dot equals to what? x2 dot equals to what? Oop, that was wrong. W dot equals to what? M1 dot equals to what? M2 dot equals to what? Yeah, -1, -1, W, M1, M1. Oh, M2, right. So that's not bad. That's what? That's x1 equals to minus t, or I guess, are we using s? Maybe s. x1 equals to minus s, x2 equals to minus s, and I guess plus a constant, right? This has got w is equal to, like, say, c3 e to the s, right? Because that's an exponential, and likewise for the m's. M1 is c4 e to the s, M2 c5 e to the s. I mean, but this is all subject to, but we're looking for, C of t. X, so much writing. Oh man, t, come on. What the? Well, he says that, but he doesn't mean it. Because he's got s everywhere below it. S, 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 S. Oy, oy, oy. So many variables. Anyway, but what's the, what should C of 0 be? Now, can you guys understand what C of 0 should be? C of 0 should be x1 of 0, x2 of 0, maybe I don't understand something here quite. Maybe the t and s are different. Oy, oy, oy. Yeah, there's an interplay between the T and the S I don't understand just yet. I'm sorry, guys. He does mean a distinction between them. Let me just summarize what happens here. So we have to understand the interplay between the T and the S, which has to do with the interplay between the curve over there in the original system and the curve on the higher dimensional system with the vector field. Once you understand that, then you can take this integral curve and it links together with the initial Cauchy data in such a way that eventually, you get the solution u of xy equal to the exponential of the square root of 2 minus parentheses x minus y squared over 2 minus parentheses x plus y over 2. And this is this function is defined in a region in the xy plane between the lines. Well, it's defined in this region, I think. This is actually the final example in the chapter, where I think he tries to draw everything together to actually solve a problem. As you can see, I have failed in my mission to actually explain the details here to you because I have not really explained what Lee's characteristic vector field is. Sorry about that. So, to be fair to you guys, I will not ask you to find the characteristic vector field. I mean, I will not ask you to solve the partial differential equations by method of characteristics, as obviously I have failed to do so today. So, just to be fair, I will strike that problem from the record and replace it with a more interesting one that we can do, which would be something like find the contact distribution for a I'll try to give you a find a contact distribution from the contact form calculation like we actually have done previous day and interested. Just give me a few hours to think about it and make it so it's actually worth doing. But let's strike the method of characteristics from the record. I had hoped we'd get to it this semester, but it just didn't happen. All right, one final thought, and then we'll be done. Well, there's not enough time for it today. So what would you like guys do? What would you guys like to do Monday? Lecture? Yeah. Good answer. Sleep. So Monday I'll either try to tell you more about this contact stuff, or the other thing I'm toying with the idea of is just spending a day to tell you about the Gauss-Bonnet theorem, which is a little bit deeper into differential geometry. I wouldn't test on it or anything. It would just be informational for you guys. But it's an interesting and deep theorem of differential geometry which marries topology and curvature. And also there's also other kinds of curvature we haven't talked about, like curvature more with respect to curves as opposed to like the surface. So curvature as opposed to surface curvature. But I think that's probably best for you guys, for me to spend the day talking about, the Gauss-Bonnet theorem, which has very, very interesting story. And we've done enough differential geometry for you guys to probably understand a good bit of it. Again, I won't test on that, but I think it's good for you to see it. And so I don't think you really need to take notes during that, so your hands should be free to eat pizza, I think, right? That sound good? Okay. So my question is, what's your preference? Yeah, I mean like pepperoni, cheese. Hawaiian? Hawaiian. You guys are. Pineapple does not belong on pizza. Haven't I taught you nothing? A lot of politics around pineapples and pizza. You can hit it. I think we're done.